All right, so starting the exponential and logarithmic function chapter of our book, we're going to first look at exponential functions, which have an x or the variable in the exponent position, and then we're going to look at the logarithmic function, which is the inverse. Inverses are necessary in order to be able to solve different sorts of functions and equations, so it's important that we study these together. Also note, and the book doesn't necessarily define them this way, but these are the first of our transcendental functions. These are the first non-algebraic polynomial functions. We've been looking at polynomial functions up until this point, so they've been either an actual polynomial function like x to the fifth or x to the fourth, kind of powers added and subtracted to each other, and then also the rational polynomial functions. So this chapter, exponential and logarithmic, starts our look into transcendental functions, which we will follow up with the sine, cosine, tangent, trigonometric graphs shortly. So looking at this, we've got 5 sections. We're going to look at 5.1, exponential functions and their graphs, applications of exponential functions. Then we'll look at the inverse logarithmic functions and their graphs, properties and applications of those logarithms, and then we're going to put them together and use them to solve equations. So I thought it was interesting, and I left this in our little preview to this chapter. What if you had to predict the amount of time it would take for the Earth's population to reach 20 billion, ignoring the effect of limited resources on population growth? This book has this as the first question to have you think about this in the chapter. I bet for future books, they will all have something like, how could you predict the amount of time that it would take a virus to spread across the world and everybody be infected? Or how would you change the graph, which is what we heard a lot with COVID. So how could you flatten the curve? Because those curves are all exponential. They actually have a calculus aspect to them, but for our purposes, they're exponential functions, and we've seen a lot of them. So I bet future books will probably have that as the opening question there. All right, so let's get started. Exponential functions. The parent function, the most basic function for an exponential function, looks like f of x equals a to the x, where a is some base, and in some books they will call this b for base, but our book calls it a, so we'll write it as a here. So a is the base, and x is obviously up here as an exponent. And because it's up here in the power position, it is called an exponential function. So we have different translations for this. Let's look at a translation and say that it could be p, and then we'll still have a to an exponent. We can have it plus or minus some shift. So we'll do minus h and then plus k. We've used h and k before. Note that this is multiplied. So in this case, this number in the front, the p, we're going to call that our initial population. That's why I'm calling it p. And this is the part that's the exponential function. And so we're going to say initial population. It's also principal when you're looking at interest problems. Up here, this x minus h is a horizontal shift. Note that because it has minus h, it's always opposite math, just like before. It's almost like this is in parentheses, but not normally written in parentheses. And then k is a vertical shift. So these translations that we've seen before, they occur here with exponential functions as well. In the parent function, note that this a that we're calling the base, a equals the base, has a rule with it. And that rule is that a must be positive and a cannot equal 1. So this is very important. We're going to set that up in advance. We can have other numbers that can be negative. We can have other numbers that are equal to 1, but a, the base of an exponential function, must always be a positive number right here, and it must not be equal to 1. And the reason for that is pretty simple. The reason that it can't be 1 is that if you had 1 to the x, then that just means that if you made an xy chart, if x is 1, you have 1 to the first, which is 1. And if you had 1, if x is 2, silly me, then you have 1 squared, which is still 1. And if you had 3, it would be 1 cubed, which is still 1. So it would not look like an exponential function if it is 1. So we can't have an exponential where we have the base equal to 1. We also can't have it be a negative number. So if we said f of x is equal to negative 2 to the x, then we come up with a different sort of issues. So I'm going to start a new xy chart. And that new xy chart is going to say, okay, what if x is 1? Then we're going to have negative 2 to the first power is negative 2. What if it was negative 2 and the exponent was 2? We'd have negative 2 squared, which is negative 2 times negative 2, which is 4. And then if you put 3 on there, you're going to have negative 2, negative 2, negative 2 is negative 8. It goes negative, positive, negative, positive. It would change from negative to positive, and your graph would go up and down. It wouldn't look like an exponential graph. So we have rules so that exponential functions have a certain look to them. And in order for that to happen, we need to have the base that is positive and not equal to 1. So here's the reason why it can't be those two things. Okay, let's take a look at other features of an exponential graph, and we'll do that with an XY chart. Okay, I want to pause right here, and I do want to talk a little bit about how to succeed in a video. If you're doing math with a video, it's very difficult to, not fall asleep, okay? So I get that. There's not a teacher telling you to pay attention. You maybe want to have some music on or something else, and I'm going to ask you for the next 20 minutes while I'm explaining things in this video if you would pay attention like you're in a math class. I need you to have paper out. You can't just watch this, you have to write it down. You can pause the video if I talk too quickly. You can rewind it and watch some more. You need to turn things off. So if you have the radio or TV on, please turn it off. Watch your Netflix while you're doing some other subject, okay? I'm asking you to pay full attention. Pause the video when I pause the video and do some work. You need to do the same. Make corrections. So if you've paused the video and worked the examples and you did something wrong, fix it when I go over it. Treat this video like an in-person class. After the video, you need to go try your practice problems and homework. Check your odd answers, find errors if you can, and rework them. That's what you should do in a normal class when the teacher says, hey, let's give it a shot. Let me know if you have any questions. You're going to have to do more work on your own and find your own questions. If you can't figure it out, you need to circle those. And when you upload them as an assignment, make a big note. Send a comment with your upload that says, I didn't understand these 3 problems. Can you go over them? Or can you look at my work and let me know what's going on? So you have the responsibility to ask more questions in this environment if you're watching this instead of being an in-person class. Okay, let's get back to this graph. I have already written down my XY chart and notice that my Y values go really high, and I've started an XY chart on the side. So please pause the video and make your own chart so you're ready to go when I start going over how to graph this. Okay, so my equation that I'm going to start with is f of x equals 2 to the x. The difference with exponential functions and the parent function is that I could have different bases here and it would still be a parent function. So I could actually have a base of 3 or 5 and it would still be the parent function for an exponential graph. But I'm going to use 2 to the x because it's a smaller number. Now, exponential functions, what that means is whatever x is, so if I said f of 3 equals, what would that mean? That would mean 2 and replace the x with 3. Oops. Sometimes when I say stuff out loud, I write that down. If the base is still 2, the exponent is now 3, what does that mean? It means 2 times 2 times 2. So I'm going to use this in order to fill out my XY chart. And every time I make a bigger number here, I'm going to have what I had before, 2 times 2 times 2, but now I've got one more. So each time you increase this, you get more numbers down here. That's what makes it an exponential function. So I've already got these two written out, f of 3 and f of 4, but they're not really where you should start with an exponential function. We do want to indicate what the starting value is. The starting or initial point is very important. So I do want to define that right here. The starting or initial point of an exponential function is the x value that makes the power 0. So looking at my power function right here, my exponential function 2 to the x, all I have to do is put a 0 there and I have 2 to the 0. Now that's important because every time you make this exponent 0, you have, so in this case it's going to be 0, 2 to the 0. You know there's a rule there that says f of 0 equals 2 to the 0. 2 to the 0 is equal to 1. So in this case, my starting position is going to be 0, 1. And you know how I like to make those into points. Now it's a point. I can put it in my chart here, 0, 1. And 0, 1 is actually the starting value in my graph. So that starting or initial point that you want to put in your XY chart here is always going to be whatever number makes the power or the exponent 0. So do make a note of this. I will ask for that periodically, and all of your graphs should start with that value. So now going through the rest of this chart, I have these two already written out. F of 3 means 2 cubed. 2 times 2 times 2 is 8. So F of 3 is 8, and 4 is going to be 16. If I go over and do the rest, let's see, plug in 1 right here. 2 to the first power is going to be 2. 2 squared is 4. And then the negative ones become interesting. So the negative values do not indicate that my graph is going to be negative. In fact, because they're exponents, this is an exponential function. If I say f of negative 1, that means 2, but then I plug in negative 1 as the exponent. And negatives and exponents mean that you need to switch it to the denominator. So this is actually still a positive number. It's a positive value, but it's a fraction. It's 1/2. So when I go and look at other powers that are negative, I'm going to have 2 to the negative 2. The negative means put 2 squared in the denominator. So that's 1/4. It's an even smaller number. Negative 3 is going to have the same power as 3, but it'll be in the denominator. So 1/8. And negative 4 will be 1 over 2 to the 4th, which is 1/16. So the numbers get smaller and smaller. There is no negative number. There's no x value that'll give a negative y value. There's no x value that can make them negative. All of these answers will be positive. And you could plug in any number that you wanted. You could plug in negative 2.5. You could plug in 3.5. We need calculators to figure out the decimals for those numbers, but the domain for an exponential graph is all real numbers. or negative infinity to infinity. So that's another thing you need to note in your information there. All right, so let's plot the rest of these points. So I've got 0, 1, 1, 2. 2 starts to grow pretty quickly to 4. 4 grows, 3. 3 grows to 8. 4 goes really quickly to 16. If I went 5, that would be 32. It would be up here somewhere. Can't even see it. And then going in the other direction, I've got -1 is 1/2. -2 is 1/4. -3 is 1/8. And they just get closer and closer to the x-axis. But as I noted before, they will not be negative. So when I connect these points, and if I keep going this way, they will just get smaller and smaller and smaller, but they'll hug the x-axis here. So we're going to call this a horizontal asymptote at 0. So just like we did with rational functions, asymptotes become a border for the graph. And it's not plural. There's just one asymptote, and it's at y equals 0. For the parent function, it may be a different value if your function has moved. So exponential graphs look like this. They grow really quickly, which is why when we're looking at a virus, we say that if it has this 2 here, for every day that passes, you would add another 2, and it grows really fast. So I'm still trying to make this darker in my graph. And we have the starting value, we have an asymptote. These are features of an exponential graph. If you were to do this same graph, but have a different function, let's say we had g of x equals 3 to the x, it would have the same starting value at 0, 1, which I'm going to add here, and then it would grow faster. So at 1, it would be at 3, at 2, it would be at 9, because 3 squared is 9. At 3, it would be at 27, so it would be up here somewhere. And it would grow even faster because it has 3 as a base. It would actually get smaller faster, but it's still going to hug the x-axis. So this would represent 3 to the x, and this darker one would represent 2 to the x. If we had another value like 1.9 to the x, it would grow at this rate, etc. Bigger numbers would hug this closer, grow faster. Smaller values would grow this way until you get to fractions. Note that I can't have a 1 here, but I could have a fraction, so I want to graph that next. One thing that I think is really important when you're looking at new things that you're trying to graph is first to note what it is. So when you look at f of x equals 1/2 to the x, first you need to note that it's an exponential function. As you get more familiar, you'll know a general idea of what that looks like, and that's going to help you out a bunch. Also, you should note domain. So domain is all real numbers. The range, I'm not sure yet. This doesn't have any shift noted over here by, it doesn't have any differences in the exponent, it doesn't have any plus or minuses, and it doesn't have an initial value. There's just a 1 understood to be right here. So domain is all real numbers. The asymptote is going to be y equals 0. You have to have the whole equation for the asymptote. So it's going to be right here, just like my other one. It's kind of hard to see, but there we go. So there's my horizontal asymptote. Now, I want to plug in first the value that makes my exponent or my power 0, and that's 0. So 1/2 to the 0 power is 1. This is the starting value, which I'm going to put a star by because it's where I'm going to start. And then I'm going to go from there and go 1, 2, 3, and then I'll go -1, -2, -3. So I'm going to do them all so you can see what happens. So we have 1/2. This is what I'm plugging in, so it's to the first power right there. 1/2 to the first power is 1/2. So at 1, I'm going up 1/2, different from my other graph. 1/2 squared, because this is what I'm plugging in for the power. So these are powers. 1/2 squared is 1/2 times 1/2. There's 2 of them, and that's 1/4. So that becomes a 0.2 1/4. 1/2 cubed means there's 3 of them. And writing this out somehow really makes it clear what an exponential means. Every time you add a new number, making this bigger, you're multiplying by whatever the base is. In this case, the base is a fraction. So whatever you had before is now halved. It's smaller. So this becomes 1 over 2 times 2 times 2, which is 1/8. So at 3, we're at 1/8. So small I can barely graph it there. Now I'm going to go in the opposite direction. From my starting value, I'm going to plug in -1. So 1/2 to the -1 means take 1/2 and flip it over. So now it's 2 over 1. I've used the negative, so it's just to the first power, and that's 2. So at -1, I go to 2. 1/2 to the -2. The negative means flip it over. So we have 2 squared, and that's 4. -2, so this is a point, -2, 4. So -2, 1, 2, 3, 4. -3 means 1/2 to the -3rd, and so that's going to be 2 cubed, which is 2 times 2 times 2, which is 8. 1, 2, 3, and I think this is 8. So here. So hopefully you have an idea that this graph is the opposite of the other graph as far as what it looks like. Its domain is all real numbers. It does have the asymptote at y equals 0. These dots will get smaller and smaller and never actually meet the dotted line, but they're going to approach it. They want to become y equals 0 desperately. They just can't get small enough. But they will never be negative. So now I can talk about the range for this one. The range goes like this. So it almost gets down here, and then it goes up infinitely over here on this side, on the negative side. So it doesn't reach 0. I'm going to write it as 0 to infinity, and I'm going to start to use my interval notation. You could also say that y is greater than 0 here. That works as well. So this is the range, but this is the asymptote, and you need to leave that as asymptote. So range and y greater than 0. All right, so this is my graph. Let's compare it to the one that we just did a minute ago. So there are different scales, so you can't compare them exactly, but they would have the same shape. It's just that the one for 1/2 is smaller in the negative numbers, whereas is larger in the negative numbers, and then 2 to the x is larger in the positive numbers. So let's review that mathematically. And if we looked at f of x equals 1/2 x to the x, if we look at g of x equals 2 to the x, we could actually rewrite that with a translation. So if I rewrite it like this, 1/2, oops, I want to actually write it with my translation. If I say 2 to the negative x, that's the same base now. So I've rewritten them so they have the same base as 2, but now the exponent is different. So I do want to talk about the translations that I've got written on this side over there for you. 1/2, if you move the 2 to the top, you have to change the exponent to be negative. And so the difference is that the one that looks like this one has a negative exponent and the other one has this positive exponent. So what that means, and I'll draw a little tiny drawing right here, and a little tiny drawing over here, as that 2 to the x grows really fast, while 1/2 to the x gets smaller. This is 0 is less than a, the base, is less than 1, and this is 1, I'll just say here, base greater than 1. So both of these are positive bases now that I've written it this way. 1/2 and 2 are both positive. 2 is positive. But if the base is less than 1, if it's a fraction, this represents decay, and this represents growth, a number bigger than 1. And the difference is in the exponent, this negative here. The negative is a horizontal flip. So this was the first one we graphed earlier in the lesson, and the negative, if you take it and flip it over this way, then you get this graph. And so this represents a translation, horizontal translation. So on in the notes on the side, I have the parent function y equals a to the x. I have the translation y equals p as a principal value times the base a times x to the x minus h. This is where we just got shifted, and then plus k is up or down. So the domain can be any x, all real numbers. That starting value, you want to start in your chart the value that makes the exponent 0. And that's because any base to 0 equals 1. So we'll look at some translations of things before you do some practice problems. All right, so let's do some actual problems that are different than the parent function. So for each of these, I want to note these key things as I work through the problems. So if your graphs are just a random sketch without noting these points, then I'll know you haven't done your work fully. So let's look. First, we have 3 as our base. We have x minus 2 as the exponent. That means the initial value. So the initial value is going to be at positive 2 something. If I plug in 2 here, I have 2 minus 2. I have 0, which is my goal. 3 to the 0 is 1. My initial starting value as at 2, 1. This means that it's normally it normally starts at 0, 1, so this is shifted to the right 2, which is what you would expect here, opposite math, 2 places. So the translation is right 2. Also, my domain, because this is an exponential function, is negative infinity to infinity. The asymptote, this doesn't have a plus or a minus anywhere, so it does not have up or down shift as an exponential function. That means it's the normal, not translated asymptote, which is at y equals 0. So I've got function, domain, asymptote is a line, starting or initial value, translation. This is going to be growth because my base is 3, which means if I look back at my examples here, it should look like a growth function. It should go up. So let's see what this looks like when I graph it. I'm going to put it here. I'm going to put the asymptote in as y equals 0. That is a part of the graph. Without it, your graph is incomplete. I need to start at 2, 1. So at 2, 1, I have a value. And then for your homework problems, you're going to need to put in 2 or 3 points to know what your graph looks like. You can't just sketch it from there. You need something that says you know what you're doing. So let's do a little XY chart. I already have 2, 1, so let's plug in values around it like 3 and 1. At 3, what happens? That's going to be 3 to the 3 minus 2. 3 to the 1 is 3. 1, 2, 3. At 3, it's at 3. At 1, it's going to be 3 to the negative 1, which is going to be 1/3. So at 1, it's at 1/3. If that's not enough for you, you should probably plug in 4. At 4, we're going to have 3 to the 4 minus 2. That's 3 squared, which is 9. 1, 2, 3, 4, 5, 6, 7, 8, 9. So here I'm at 9, and I can see it from there. And this one follows the asymptote this way. And there's your function. You need to have 2 or 3 points. You need to have this point. This is your starting point. You must find the value that makes the power or the exponent 0. That's the place where it changes from really slow growth to exponential growth. Now you're actually multiplying by 3, by 3, by 3, and it grows really quickly. So this one has a base of 3. It has a shift of right 2, and then standard exponential growth there. All right, for my second example, I've got f of x equals 5 to the x minus 2 plus 3. So write that down. Then you want to make notes of the things that you know. This is exponential. It's going to be growth because the base is 5. So the base is 5. This represents growth. It has a shift. This is also right 2. So this is right 2, which means the initial value, the starting value, is going to be at 2. And if I plug in 2, I'm going to have 5 to the 0. That's 1. 1 plus 3 is 4. So I have a starting point of 2, 4. I have a vertical shift of 3. This is up 3. That means that the horizontal asymptote is now at y equals 3. So that's something new for us here. So when I draw my xy chart, I'm going to have 1, 2, 3. We're going to have a horizontal asymptote where it crosses the y-axis at 3. That means my graph will never go below y equals 3. And I've got a point 2, 4, which is here, 2, 4. Now, I could kind of sketch this out. I know it's probably going to look like this because it's growth. You need to plot some points so that you know that for sure. So let's plot some points around 2. So let's plot 3 and 4 and then 1 again. So at 3, I'm going to have 5. 3 minus 2 is 5 to the 1 plus 3, that's 8. So at 3, I've got 4, 5, 6, 7, 8. And then at 4, I've got 5 to the 4 minus 2, because that's where I'm putting 4. 4 minus 2 is 2, plus 3, that's 28. So that's really high up here. It won't even really probably fit on my graph, but I'll estimate it to be there. And then at 1, I've got 5 to the 1 minus 2 plus 3. That's 5 to the negative 1 plus 3, which really means 1/5 plus 3. So that means 3 and 1/5. That's really small. That's going to be here at 1, and it's going to be 1, 2, 3, and a little bit. So it's right there, right above the asymptote. So here now we have enough points to graph, and voila, we have a graph. So this graph, because it has plus 3, this is a positive number, plus 3. It can never be down here in the negatives. We didn't talk about domain, but domain, again, is all real numbers because this is an exponential graph. And I'm going to keep writing that because I want it to be very clear to you that exponentials have domain of all real numbers. That's really important as we go forward. Now that we have it graphed, it's easy to see the range. And the range goes almost to positive 3, but doesn't include 3, and then it goes up to infinity. So that soft bracket there is important, and it goes to infinity. So domain and range. So you have several graphs to try. Some of them have flipped x's, and so you're going to need to think about what that does to your graph. In other words, if we had g of x equals, let's see, if we had 3, let's do this one, 3 times 2 to the negative x, what does that actually mean? That means that this graph is going to be flipped. So this is the initial quantity. This is our base, 2, and it's to the negative x. What does that really mean? It means that we have 3 times 1/2 to the x. So this one's going to be decay. This negative has flipped our graph horizontally. So instead of looking like growth, it will look like decay. So this one will be decay. And the negative x is what flipped that. So our starting value is going to be 0. When we plug in 0, we have 3 times 1/2 to the 0, or 3 times 1 is 3. So this has been multiplied by 3 or shifted up by 3. And so I'll go ahead and graph this one. It does not have a horizontal shift, a vertical shift. There's no plus k. Therefore, the asymptote is going to be here at 0. So y equals 0 is the asymptote. You do have to graph it. And my starting value is at 0, 1, 2, 3. And then when we plug in some values to see that decay, we can plug in -1. That will be 3. I'm going to plug into the original. So that'll be 2 to the -1. 3 times 2 to the first is going to be 6. So at -1, we're at 1, 2, 3, 4, 5, 6. You can see it goes up. And then if I plug in +1, I'll have 3 to the 2 to the negative, 3 times 2 to the negative, but I'm plugging in a 1 here. That's going to be 3 times 1/2, or 3/2. So at 1, I'm at 1.5. And then at 2, I'm going to be at 3. 2 to the -2, so I'm plugging into this original equation, -2. That'll be 3 times 1/4, which is 3/4. So at 2, I'm at 3/4. And if I wanted to plug in another number over here, like -2, just to see that growth, that would give me, here's my original function, 3, 2 to the negative. So 3 times 2, negative, this original function, but I'm going to plug in -2 here. That becomes 3. 2 to the second power, which is 4, which becomes 12. So at -2, I'm at 12. And it's going to follow the asymptote right there. All exponential functions have an asymptote. And so you have to include that in your graph. So I didn't really talk about the shifts here. I can say this has horizontal flip. It has a stretch factor of 3, that initial condition that we started with. I have my initial point that I started with here. It's the first point that I graphed, and the asymptote didn't shift, so it's at y equals 0, and I didn't write that down, so here it is, y equals 0. So these things are important. Your domain is all real numbers. So your first practice is graphing these and being able to pick out the important features. If your book does not suggest that you write all of these things down, I'm asking you to. So I want to be able to see all of that. If your graphs look like this, then that doesn't count for anything. You need to have all the important features of an exponential graph with your practice work. And then let me know if you have any questions. Thanks.